Consider learning to drive a car from raw pixel inputs. A model-free agent must connect a pattern of pixels to a successful action, like turning the wheel, through countless trials. This mapping is incredibly complex and brittle. If the lighting changes, the entire policy might fail. The core problem is that raw observations, like images, are high-dimensional and contain redundant information. A world model's first job is to distill this sensory stream into a compact representation of the environment's true state, separating style from content. Reinforcement learning is broadly divided into two paradigms. Model-free methods, like DQN or PPO, directly learn a policy or a value function. They are robust but learn through brute force correlation. Model-based RL, conversely, first learns a model of the environment's dynamics, a function that predicts the next state and reward. This world model can then be used for planning, allowing the agent to simulate outcomes before acting. World models are a powerful, modern take on this, learning the dynamics model not in pixel space, but in a compressed latent space. The world model hypothesis, articulated by Ha and Schmidhuber, proposes a division of labor. Instead of one monolithic network, the agent is composed of three distinct components. First, a vision model compresses the raw, high-dimensional observations into a compact latent vector. Second, a memory model acts as the world model itself, predicting how this latent vector will evolve over time. Finally, a separate, and often very simple, controller makes decisions using the outputs of the vision and memory models. This separation is key to its success. Let's formalize this. The vision model V is typically a variational autoencoder, or V. It encodes an observation OT into a latent vector ZT. The memory model ME is a recurrent neural network, often an LSTM, with a mixture density network output layer. It models the probabilistic transition PZT1ZT, a T, HT. The controller C is a remarkably simple linear model that maps the concatenation of the latent state ZT and the RNN's hidden state HT to an action a T. Each component is trained separately, which simplifies the learning process. The VAE's role is unsupervised compression. It's trained on a dataset of random experiences from the environment, without any regard for rewards or tasks. Its goal is to learn a mapping from a high-dimensional observation O to a low-dimensional latent vector Z that captures the essential spatial features of the scene. The VAE is trained to minimize a reconstruction loss plus a KL divergence term, which regularizes the latent space to follow a standard normal distribution. This structured latent space is crucial for the memory model to learn from. The memory model is the heart of the system. It's an RNN trained to predict the next latent code, ZT1, given the current latent code ZT, the action a T taken, and its own hidden state HT. The environment can be stochastic, so a deterministic prediction isn't enough. This is why it uses a mixture density network MDN as its output layer. Instead of predicting a single ZT1, it predicts the parameters means, standard deviations, and mixing coefficients off a Gaussian mixture model, representing a full probability distribution over possible next states. Surprisingly, the controller can be extremely simple. The original paper used a linear model with only 867 parameters. It computes an action a T as a linear function of the current latent code ZT and the RNN's hidden state HT. The hidden state HT provides a summary of past events, granting the agent a form of memory. This tiny controller is not trained with backpropagation. Instead, its weights are found using an evolution strategy like covariance matrix adaptation evolution strategy, or CMAEs, which is highly parallelizable. This is where the magic happens. Once the VAE and MDN-RNN are trained, we can largely ignore the real environment. The controller is trained entirely within an imagined environment generated by the MDN-RNN. The process starts with a real Z0 from the VAE. The controller suggests an action A0. The MDN-RNN then predicts a distribution for Z1 from which we sample. This new Z1 and the updated hidden state are fed back to the controller. This loop of prediction and action selection generates entire dream trajectories, and the controller is optimized to maximize the cumulative reward within these dreams. The original World Models paper showed the power of this architecture, but training the controller with evolution strategies can be inefficient. The next major step was PLA-NET, latent dynamics for planning. Instead of learning a separate policy network, PLA-NET uses the learned world model directly for online planning. At each time step, the agent considers a sequence of possible future actions, simulates their outcomes using the world model, and executes the first action of the sequence that leads to the highest predicted reward. This replaces the separate controller with a more direct planning mechanism. PLA-NET introduced a more sophisticated state space model, the recurrent state space model, or RSSM. A key innovation is splitting the state into a deterministic part, HT, and a stochastic part, ST. The deterministic path, an RNN, summarizes past information. The stochastic path models the uncertainty and randomness inherent in the environment. At each step, the model computes a posterior belief about the current state ST based on the new observation, and a prior belief based only on the past. The model is trained to make the prior and posterior beliefs consistent. So how does PLA-NET plan? It uses a sampling-based planning algorithm called the cross-entropy method, or SEM. At each step, it starts with a distribution over action sequences, for example, a Gaussian. It samples a batch of candidate action sequences from this distribution. Each sequence is rolled out in the latent space using the learned dynamics model, and the total predicted reward is calculated. The top best sequences are identified, and the distribution over actions is refitted to this elite set. After a few iterations, the mean of the final distribution is used as the plan, and the first action is executed. PLA-NET was a major advance, achieving state-of-the-art performance on many control tasks. However, its online planning with CEM at every time step can be computationally expensive and may not discover complex, long-horizon behaviors. This led to Dreamer. Dreamer combines the best of both worlds. It uses the learned world model to generate imagined trajectories, but instead of planning from scratch each time, it learns a persistent actor-critic policy within this imagined environment. It's learning a policy from dreams, not just using dreams to pick the next action. Here's how Dreamer learns. First, the world model is trained on real experience, just like in PLA-NET. Then, the imagination phase begins. The agent uses its current policy to generate long trajectories purely within the latent dynamics model. A value function, or critic, is trained on these imagined trajectories to predict the expected future rewards. The policy network, or actor, is then updated using gradients from this value function, encouraging actions that lead to high-value states. This is a standard actor-critic update, but the crucial difference is that the data comes from the model, not the real world. Dreamer v2 made a key architectural change that significantly improved performance and stability. It replaced the Gaussian latent variables of the RSSM with discrete, categorical variables. Instead of a single vector ST, the latent state is represented as a set of categorical distributions, say 32 variables, each with 32 possible classes. This allows the model to represent more complex, multimodal, and even discontinuous dynamics. Because sampling from a categorical distribution is non-differentiable, it uses the straight-through estimator trick to pass gradients during training. This change enabled Dreamer v2 to master the Atari benchmark from pixels, a first for a model-based agent. Dreamer v3 focused on scaling and robustness. It introduced a few key modifications to make the algorithm work out of the box across a vast range of domains with fixed hyperparameters. These include sim-log scaling for rewards and values to handle different reward magnitudes, KL balancing to prevent one part of the latent state from dominating the learning signal, and a separate critic for the actor's learning objective. These tweaks, while seemingly minor, created a general and scalable algorithm that excelled not only in standard benchmarks but also in sparse reward tasks, and even acquired Minecraft diamonds from scratch, a major milestone. The impact of world models extends far beyond game benchmarks. In robotics, they offer a path to mitigating the sim-to-real gap. An agent can learn a general world model in a simulator and then fine-tune it with a small amount of real-world data, drastically reducing physical interaction time. In autonomous driving, predictive world models are crucial for anticipating the behavior of other vehicles and pedestrians. They can also be used for creative applications, generating novel content by dreaming within a learned model of a data distribution, such as music or images. Despite their successes, world models face significant challenges. The most prominent is compounding error. Small prediction errors made by the dynamics model at each step can accumulate over long imagined trajectories. After many steps, the imagined state can diverge drastically from any plausible real-world state, a phenomenon known as drifting off the manifold of reality. The controller might then learn to exploit flaws in the simulated physics, leading to policies that are brilliant in the dream but catastrophic in reality. Keeping these imagined rollouts grounded is an active area of research. Closely related is the problem of model mismatch. The world model is, by definition, an imperfect approximation of the real environment. It might fail to capture certain, rare but critical events or oversimplify complex dynamics. A policy trained exclusively in this flawed model may not be robust when deployed in the real world. Techniques like injecting noise during imagination, assembling multiple world models, or periodically collecting more real-world data in areas where the model is uncertain, are used to mitigate this. The goal is to make the agent aware of its own model's imperfections. Many real-world tasks are partially observable. A single observation, like a camera image, may not reveal the full state of the environment. For example, an agent can't know the velocity of an object from a single static frame. This is where the recurrent nature of models like the RSSM is essential. The deterministic hidden state HT acts as a memory, integrating information over time to build a more complete belief about the true underlying state. This allows the agent to infer things like velocity, momentum, and hidden causal factors that are not immediately visible. A major frontier for world models is moving beyond unstructured latent spaces towards more interpretable and compositional representations. Object-centric learning aims to build world models that explicitly represent individual objects, their properties, and their interactions. Instead of a single latent vector ZT, the state would be a set of vectors, one for each object in the scene. Such models could generalize far better, as they could reason about novel combinations of familiar objects and understand the underlying causal physics of the world, rather than just memorizing pixel patterns. Another exciting direction is hierarchical planning. Current models plan at the level of primitive actions: turn left, move forward. Humans, however, plan abstractly: go to the kitchen, then make coffee. Future world models could be trained at multiple temporal scales. A high-level model might dream in terms of abstract goals, which a low-level model then translates into concrete actions. This would allow agents to solve much longer horizon tasks by breaking them down into manageable sub-problems, a key component of scalable and intelligent behavior. We've journeyed from the foundational three-part architecture of the original World Models paper, VAE, MDN-RNN, and controller to the sophisticated planning of PLA-NET's RSSM, and finally to the policy learning and imagination of the Dreamer series. The core takeaway is the power of separating the problem. First, learn a compressed, predictive model of the world from sensory data. Then, use this fast, parallelizable, and differentiable model to efficiently learn complex behaviors. This approach has proven to be one of the most sample-efficient paradigms in modern reinforcement learning. World models represent a fundamental step towards agents that can understand and reason about their environment. By giving agents an imagination, we allow them to learn from simulated experience that is faster, safer, and more abundant than real-world interaction. While challenges like compounding error and model mismatch remain, the rapid progress in this field suggests that learning to dream may be a critical part of the path towards more general and capable artificial intelligence. Thank you for watching.